strong electrolytes as well as the weak electrolytes. First, let us see the electrolyte. What is an electrolyte? We have to see electrolyte in the second year. There is a chapter, electrochemistry. In electrochemistry, the term electrolyte is coming again. So electrolyte is a substance which ionizes in solution. It ionizes in solution, forming positive and negative ions, and conducts electricity. And such materials are electrolytes. Electrolytes can be classified into two types: strong electrolytes and weak electrolytes. As I mentioned, strong electrolytes, they have a high degree of ionization or dissociation. Strong electrolytes, they ionize strongly. Strong electrolyte ionizes. It ionizes strongly. That means more ions are produced in solution. So they can conduct electricity easily. And such electrolytes are strong electrolytes. Say, for example, sodium chloride, Na plus Cl minus, or sodium acetate, CH3COO minus Na plus. Say, all these are composed of ions. They are composed of ions. These are ionic solids. And so they ionize easily. Producing, say, large number of ions, and they can conduct electricity easily. And they are strong electrolytes. But what about the weak electrolytes? A weak electrolyte is one which ionizes weakly. Say, very weak ionization, feeble ionization. Only the small extent of ionization. So a small number of ions will be produced in solution. That means they are not completely ionized in solution. While the strong electrolytes are completely ionized. We can say like this. They are ionized completely. They are completely ionized in solution. So there will be a large number of ions. That is in the case of a strong electrolyte. But in the weak electrolytes, the ionization is not complete. Not completely ionized in solution. Not completely ionized. So ionization is very poor. So there will be only a small amount of ions. And these are called weak electrolytes. For example, acetic acid, CH3COOH. It is not composed of ions. But when you prepare a solution, acetic acid is slowly ionized, giving acetate ion and H plus ion. Similarly, ammonium hydroxide, NH4OH, that is a weak electrolyte. When solution is prepared, ammonium hydroxide is ionized into NH4 plus ion and OH minus ions. So these are weak electrolytes. So we can classify electrolytes into strong electrolytes and weak electrolytes. These are not required for the first year, but we need this for the second year. So you think of a weak electrolyte, for example, weak acid. Acetic acid is a weak acid. The ionization is very poor. Very low ionization, very low ionization. So it is weak acid is a weak electrolyte. Okay. Now you consider the ionization of a weak electrolyte. We are going to see the common ion effect. The common ion effect. Think of the ionization of a weak electrolyte. Say, for example, CH3, COOH, acetic acid. That is a weak electrolyte. It's a weak acid. It is a weak electrolyte. And when a solution is prepared, say it slowly ionizes, weakly ionizes, giving H plus ion and CH3, COO minus ion, acetate ion. Acetate ion. So the ionization is only to a small extent. Only a fraction is ionized. The fraction that is ionized, that is called the degree of dissociation or a degree of ionization alpha that we have studied in the last class. The fraction of a weak electrolyte ionized or dissociated, that is called the degree of dissociation or a degree of ionization alpha. And we had seen a relation between the dissociation constant of an acid Ka and the degree of dissociation alpha. And the relation was, we had seen in the last class, Ka is equal to C alpha squared by 1 minus alpha, where C is the initial concentration of the electrolyte, the weak electrolyte. Now you consider this weak electrolyte acetic acid. The ionization is only to a small extent. Now you add a strong electrolyte, for example, sodium acetate, CH3, COO, Na. It consists of CH3COO minus Na plus. It is ionic. And this is our sodium acetate. Sodium nitrate, sodium sulfate, similarly sodium acetate. Sodium acetate. And this is a strong electrolyte. Say, strong electrolyte. As we have seen, a strong electrolyte, it dissociates or ionizes completely only the forward reaction. It is not reversible. And you will get CH3COO minus ion plus Na plus ion. The dissociation is almost complete. It is a strong electrolyte. When the strong electrolyte sodium acetate is added, what happens to the dissociation, the ionization of the weak electrolyte? You know, the dissociation, the ionization of the weak electrolyte is suppressed. That means the backward reaction becomes faster. The backward reaction increases. Ionization is suppressed. Ionization is suppressed means the formation of ion that is decreased. That means the forward reaction is decreased. The backward reaction, the reverse reaction is increased. When the reverse reaction is increased, the dissociation or ionization is suppressed. So the dissociation of a weak electrolyte is suppressed by the addition of a strong electrolyte containing a common ion. That is called a common ion effect. Say, in the weak electrolyte here, acetic acid, there is acetate ion. And in the strong electrolyte, sodium acetate here, there is the acetate ion. Both the electrolytes contain the common ion, acetate ion. So, by the addition of a strong electrolyte containing a common ion, the dissociation of the ionization of the weak electrolyte can be suppressed. The backward reaction is increased. Ionization is decreased. And that is called the common ion effect. See here, when sodium acetate, a strong electrolyte is added into acetic acid solution, which is a weak electrolyte, the dissociation of the weak electrolyte, namely acetic acid, is suppressed. And that is an example for common ion effect. We have to see some examples, some applications. So, for example, you take a saturated solution of sodium chloride. In the sodium chloride solution, there will be sodium ions and chloride ions. Strictly speaking, sodium chloride is a strong electrolyte, no doubt. But if we pass hydrogen chloride gas through sodium chloride solution, say a solution of a sodium chloride, you pass hydrogen chloride gas. Hydrogen chloride is a stronger electrolyte. Hydrochloric acid, that is a stronger electrolyte. So HCl, stronger than NaCl. And HCl ionizes, giving H plus and Cl minus ions. See here, there is a common ion. Here chloride ion is the common ion. So when HCl, a stronger electrolyte, is passed through a saturated solution of sodium chloride, the dissociation of sodium chloride is suppressed. The dissociation of a sodium chloride is suppressed. And so what happens? The backward reaction is increased. That means the dissociation of NaCl is suppressed, or the reunion of Na plus and Cl minus is increased. And so there is formation of sodium chloride. It's a saturated solution. And due to the suppression of sodium chloride will be precipitated. Sodium chloride is precipitated. Hence, we can purify sodium chloride by passing hydrogen chloride gas through sodium chloride. So, the purification of sodium chloride, by passing hydrogen chloride gas through a solution of sodium chloride. There is precipitation of a pure sodium chloride. And in the purification of sodium chloride, we can see common ion effect. So purification of sodium chloride by passing hydrogen chloride gas through an aqueous solution of sodium chloride, NaCl solution. That is by common ion effect. It's an example for common ion effect. The purification of sodium chloride by passing hydrogen chloride gas through sodium chloride solution. It's an example for common ion effect. See here, hydrogen chloride is a stronger electrolyte than NaCl. So when HCl is passed, the dissociation of NaCl is suppressed and the pure sodium chloride is precipitated. And that is the application of a common ion effect in the purification of sodium chloride. So sodium chloride is purified by passing hydrogen chloride gas to sodium chloride solution by common ion effect. Here the common ion is chloride ion. Similarly, salting out of soap. Soap is sodium or potassium salt. Sodium or potassium salt of a fatty acid. Fatty acid. So it is sodium salt or potassium salt. If you add sodium chloride into soap solution, soap will be precipitated. That is because here sodium chloride is a stronger electrolyte. By the addition of a stronger electrolyte, sodium chloride, the dissociation of the sodium salt or fatty acid or soap is suppressed, and there is precipitation of soap. The process is called salting out. Salting out. Salting out of soap. Salting out of soap. Soap is precipitated by the addition of a common salt, sodium chloride. And that is also an application of a common ion effect. So in general, the dissociation of a weak electrolyte can be suppressed by the addition of a stronger electrolyte containing a common ion. That's called the common ion effect. We have seen, say, 2 examples here. There is one more point to see in this chapter, and it is a solubility product. Solubility product. Solubility product. KSP. KSP. K, that is a constant. K, solubility product is a constant. So K, constant. SP, solubility product. SP for solubility product. You take a sparingly soluble salt. A sparingly soluble salt. Sparingly soluble salt. Sparingly soluble means it is somewhat insoluble. It is somewhat insoluble. Say, for example, you take silver chloride, AgCl. That is somewhat, it is insoluble in water. Insoluble means the solubility is only very low solubility. Similarly, barium sulfate, that is a white precipitate, and that is precipitate. Precipitate means solubility is very low. Silver chloride is also a white precipitate, that is sparingly soluble. A salt is sparingly soluble means it is somewhat insoluble. It is insoluble. It will be precipitated. So the solubility is only very low value. It dissolves only to a very small extent. And if we get a saturated solution of a sparingly soluble salt, you take a saturated solution of a sparingly soluble salt, It is a very dilute, it's a very dilute solution. It's a very dilute solution. And so, it's a very dilute solution. And so, the electrolyte dissolved is completely ionized. It's a very extremely dilute solution. The solution of a sparingly soluble salt is extremely dilute solution. Extremely, because the salt is insoluble in water. Sparingly soluble means solubility is very low. It is insoluble. It will be precipitated. Even then, a very minute amount will dissolve. A minute amount will dissolve. And the saturated solution of a sparingly soluble salt It is an extremely dilute solution, and therefore the salt dissolved is completely ionized. For example, you take a barium chloride. Barium chloride. It's a very dilute solution, and you will get Ag plus a Cl minus ions. You know, silver chloride is sparingly soluble. It will not dissolve to an appreciable amount. Only very, very small amount, negligibly small amount of so AgCl will dissolve in water. And so the solution of AgCl, sparingly soluble salt AgCl, is extremely dilute. And therefore, the whole of the salt dissolved is completely ionized. So AgCl dissolved is completely ionized. Now, there is an equilibrium in the saturated solution. There is an equilibrium. Now you take the product between the concentrations of the ions. It is called the solubility product. So, solubility product of a silver chloride is equal to the product of the concentrations of Ag plus ion and Cl minus ion. Cl minus ion. So it is the product of, say here, it is the product of the concentrations, the product of the concentrations of the ions, in a saturated solution. In a saturated solution. You know, in the saturated solution, there will be the maximum amount of positive and negative ions. So that the concentrations of the ions will remain a constant. You know, at equilibrium, the concentrations remain the same. Concentrations remain unchanged. So concentration here, you take AgCl, concentration of Ag plus, it remains a constant. Concentration of a Cl minus, it remains a constant. So you take the product of the concentrations, that also will be a constant. And that is called the solubility product of AgCl. So Ksp of AgCl is equal to concentration of Ag plus into concentration Cl minus. So in general, solubility product of a sparingly soluble salt is the product of the concentrations of the ions. I repeat, ions. Concentrations of the ions in the saturated solution. Product of the concentrations of the ions in the saturated solution. So the concentrations will be constant. So the product is also a constant. So Ksp is a constant at constant temperature. Similarly, you take a barium sulfate. That is also a sparingly soluble salt. And if it dissolves, we get a very dilute solution. And there will be Ba plus 2 ion plus SO4 minus 2 ion. It's a saturated solution. Even if it is a saturated solution, it is a very dilute solution. You know, in the saturated solution, there will be the maximum amount of the solute dissolved. No more solute can dissolve in that solution. And that is a saturated solution. So, in a saturated solution, no more solute can dissolve at that particular temperature. It has reached the maximum amount. The solute has dissolved to the maximum amount. It's a saturated solution. Now you come to barium sulfate. It's a sparingly soluble salt. It is precipitated, and therefore the solution of barium sulfate, even if it is a saturated solution, it is an extremely dilute solution, and therefore we can believe that barium sulfate dissolved is completely ionized to Ba plus 2 and the SO4 minus 2 ions. So that the concentrations of Ba plus 2 and the SO4 minus 2 remain constant. The concentrations remain constant. Now you take the product between the concentrations of barium ions and the concentrations of sulfate ions. That product will be a constant, and it is called the solubility product of barium sulfate. So the solubility product is the concentration, the product of the concentrations of the ions in a saturated solution. It's a constant. It depends on temperature. When temperature changes, solubility product also changes. Let us take another example. Say FeOH twice, ferric hydroxide. Ferric hydroxide. It will be precipitated. It will be precipitated. It's a precipitate. That means it is a sparingly soluble salt. So the saturated solution of ferric hydroxide will be an extremely dilute solution. And the ions formed will be Fe plus 3 ions plus 3 OH minus ions. 3 OH minus ions. And you take the product of the concentrations of the ions, and it is the solubility product of ferric hydroxide. C equal to concentration of Fe plus 3 in the saturated solution into concentration of OH minus, and here there are 3 OH minus ions. So you take the cube, say OH minus raised to 3. So in the product, the concentration terms are to be raised to the power of the coefficient. It is to be raised to the power of the coefficient. See? It is like this. Okay. You take a magnesium hydroxide. Magnesium hydroxide. It is a sparingly soluble salt. And in the solution, it ionizes into Mg plus 2 and the 2 OH minus ions. So the solubility product, the KSP, is equal to concentration of, say, Mg plus 2 into concentration of OH minus raised to the power of the coefficient 2 squared. Say like this. Do you remember the calculation of the equilibrium constant? In the calculation of the equilibrium constant, the concentration terms are raised to the power of the coefficient. Is it not? Similarly, here also, we have to raise the concentration terms to the power of the coefficient, but we have to consider only the ions on the right-hand side. That is solubility product. Now, when solubility product same as a constant, I told you, when the ionic products, that is product of the concentrations of the ions, exceeds, ionic product exceeds the solubility product, then precipitation occurs. Precipitation occurs. Because this product should be a constant. The product should be a constant. If the product of the concentrations of the ions, that is called the ionic product. The product of the concentrations of the ions, that is called the ionic product. Do you know ionic product of water? Concentration of H plus into concentration of OH minus. Ionic product. So the product of the concentrations of the ions raised to the power of the coefficients, that is called the ionic product. When ionic product exceeds, becomes greater than the solubility product, then precipitation of the solute occurs. This is because solubility products should be a constant. So to maintain the solubility product a constant, if an ionic product increases, then the precipitation of the solute begins. So in general, when the ionic product of the ions increases, then the precipitation increases or becomes greater than the solubility product, then precipitation occurs. This we can apply in the case of sodium chloride. You take a saturated solution of sodium chloride, it ionizes into Na plus and Cl minus ions. Now, what is the solubility product of a sodium chloride? Solubility product of a sodium chloride is equal to, you can say what it is, that is concentration of Na plus into concentration of Cl minus. That is the solubility product of sodium chloride. Now you pass hydrogen chloride gas through this. Then hydrogen chloride ionizes, giving H plus and Cl minus ions. So now what happens to the total concentration of the ions? The concentration, say here, the concentration of Cl minus increases. The total concentration of a Cl minus increases, but the product of Na plus and the Cl minus, that should be a constant. So to keep the solubility product of sodium chloride a constant, the concentration of Na plus is to be decreased. The product should be a constant. Concentration of Na plus into concentration of Cl minus, that should be a constant at constant temperature. And we are passing HCl. When HCl is passed, more Cl minus ions are produced. So the total concentration of Cl minus increases. So the product between Na plus and the Cl minus, Na plus and the Cl minus, that is the ionic product. It becomes greater than the solubility product Ksp, because Ksp should be a constant. So to keep Ksp a constant, the concentration of Na plus should be decreased, because Cl minus is increased. The product should be a constant. Cl minus is increased. To keep the product a constant, Na plus should be removed from the solution. And Na plus is removed from the solution in the form of sodium chloride. So there is precipitation of sodium chloride. Say, sodium chloride precipitates when HCl is passed through a saturated solution of sodium chloride. And that is to keep the solubility product a constant. So we can explain the purification of sodium chloride in two ways, either in terms of the common ion effect or in terms of the solubility product. We can explain two ways, common ion effect or solubility product. We can give the explanation two ways. In the common ion effect, and what is the principle behind the common ion effect? The precipitation of sodium chloride occurs. Precipitation of sodium chloride occurs when a strong electrolyte containing a common ion is added. For example, HCl is added. Then there is precipitation, common ion effect. That is one explanation for the precipitation or purification of sodium chloride. We can explain the precipitation of sodium chloride in terms of the solubility product also. Say we have a saturated solution of sodium chloride And the solubility product of sodium chloride is equal to concentration of Na plus into concentration of Cl minus. When SCl is passed, from SCl, more Cl minus ions are produced. So the total concentration of Cl minus increases. So what will happen to the ionic product of sodium chloride? Concentration of Na plus into concentration of Cl minus, that becomes higher value. It becomes greater than the solubility product. But solubility product should be kept a constant. The product between Na plus and Cl minus, it should be kept a constant. So to keep the product a constant, solubility product a constant, Na plus is to be removed from the solution because concentration of Cl minus is increased. So Na plus is to be removed out. And Na plus is thrown out from the solution in the form of sodium chloride. So there is precipitation of sodium chloride when HCl gas is passed through sodium chloride solution. So the precipitation or purification of a sodium chloride can be explained in two ways, either in terms of the common ion effect or in terms of the solubility product. I told you, when the ionic product becomes greater than the solubility product, precipitation occurs because solubility product should be maintained a constant. So to keep the solubility product a constant, some more the solute is to be thrown out from the solution, and there is precipitation or a crystallization. And that is the theory behind the purification of sodium chloride by passing HCl through sodium chloride solution. So we can explain in two ways, common ion effect or by the solubility terms also. Or we can explain that in terms of the Le-Chatelier principle also. Le-Chatelier principle. The concentration Cl minus increases, backward reaction increases. When Cl minus increases, backward reaction increases, and the NaCl is precipitated. So we can give the explanation in various ways. There is precipitation of sodium chloride when HCl is passed through NaCl solution, and that is explained in various ways by the application of the Le-Chatelier principle, by the application of the common ion effect, by the application of the solubility product also. And so it finishes the chapter equilibrium. Only a limited number of problems we have worked out, and that is mainly on the hydrogen ion concentration. Hydrogen ion concentration, that is pH value. You study only that much. But all these things are necessary for